Hello, I'm going to make a video today where I talk a little bit about energy. Um, so let's say, and specifically I'm going to be talking about physical, I don't know how to say this, mechanical energy, I guess, as opposed to like heat energy or electrical energy. I'm just going to be talking about mechanical energy at the moment. And so I want to talk about physics in general. Um, I feel like maybe sometimes the way that physics is presented, people learning physics can end up kind of missing the point sometimes or not making certain key connections. And so I want to try to make some of those connections. That's really what I like to do. So for this right here, let's imagine that we have some kind of a block. I don't know. There we go. All right. So we're going to say that we have this cube. And the mass of this cube is going to be equal to 5 kilograms. Draw a little bit slow on a tablet here. So let's say that the mass equals 5 kilograms. So that just tells us, for explanatory purposes, how heavy it is. Obviously, that's not what it technically represents, but for explaining purposes, it's basically how heavy this object is. Yeah. So that's it's a property of this object, and you can do different kinds of things to this object, but when you do those things, it's still going to have this same property of this much mass, which technically is how much stuff is in it, but it's easier, I think, conceptually to think about how much it weighs because we deal with that on a regular basis, and it's close because they're proportional. So anyway, so that's this measurement here. And if we imagine it stationary, then that's the only thing. As far as physical objects, that's the only object we have to deal with at the moment. But let's say that we imagine this object in some different scenarios. And so the first one is, let's put this on the left here. So let's say that we imagine this object. I'm going to redraw it again. And so this is the same cube, but here maybe I could have been holding it in my hand, I could have had it sitting on my desk or something. Here I'm going to imagine that it's suspended in the air. So this is the shadow that it casts on the ground. And now I want to so yeah, here's this object. Imagine it's not see-through. I just drew it kind of see-through, but it casts a full shadow on the ground, and it has a certain height above the ground. And I'll just put some numbers in. You wouldn't need them, but I think it helps conceptualize. So let's say that we imagine that this is 2 meters off the ground. I'm going to stick with SI units because they're a little more convenient for physics. I like doing physics with SI units. So once again, the mass of this object hasn't changed. It's still 5 kilograms. Okay, and then there's another property that we have here, which actually would be used to finish out the weight, but I wasn't really trying to talk about weight in this video. So there's a force that's acting on this object if it's suspended in the air above the earth. The force pushes it downward towards the earth. Technically it's towards the center of the earth, but if you imagine this like in your hand or visible right in front of you, you can think of it as going down. So the force pushes this downwards towards the earth, and the force causes an acceleration on this block, and the acceleration that it's going to cause is going to be g, which is a constant acceleration that has to do with the acceleration that is an object feels that is relatively close to the center of the earth. So like not out in orbit, basically close enough that dealing with regular human distances from the center of the Earth, then g equals this same value. The acceleration caused by gravity equals this value g, which is 9.8 meters per second squared. So meters per second squared is the unit of acceleration. And in case I have anybody watching my video that's not familiar with metric units, well, I guess it would be miles per hour squared, but we don't really use that either. I guess in regular speech, I don't think we talk about acceleration in terms of units. I just don't think it comes up much, like say for a kid who deals with regular everyday life. So this unit represents the acceleration. So it's the change in the speed that is being enacted on this object by the force. Okay, so this right here, we have these three values in this setup I just made. There's other things that are going on in this setup. If this were reality, the block might have temperature, for example. What else? There could be many other properties too, but for right now, if we imagine this setup, we're only considering these three properties: the height that the object is from the Earth, the acceleration that is put onto the object by the force of gravity, which is a constant value. It's g. It's always 9.8. And then the mass of the object, which this particular object, the mass is always going to be 5 kilograms, unless you start to chip away some of it or something like that. But under pretty normal circumstances, the mass is always going to be 5 kilograms for this object. But if you had a different object, it could be a 10 kilogram object, it could be a 3 kilogram object. And then as far as the height here, we're imagining that this object is 2 meters high, but it could easily also be 10 meters high or 1 meter high. So that's kind of what's going on. So the one that really doesn't change is this g. The ones that do change more readily, more easily, could be changed for the setup of the problem are the mass and the height, which should have been h. And I didn't save myself enough room, so we'll say h equals, so that's h equals 2 meters, height equals 2 meters. Now what we have here is we have three different numerical values, and we can describe the relationship between these three values. So these three values will always have, in this given setup, the same relationship between the three values. And that relationship can be expressed mathematically as an equation or a formula, or to be honest, I think in physics it's better just to use the term relationship. I think it helps make some of what you do with them more clear. So the relationship between these three values, we say that, I guess there's a fourth value that I didn't write yet. So when we multiply all these three values together, that it is equal to a fourth value, and we'll call that value potential energy. And a couple reasons I wanted to set it up that way. One, I'm convinced that energy actually does not represent any reality, but it is rather just a theoretical framework to discuss realities. So what I mean by that is mass, in my opinion, the way I understand reality, physics, mass is a physical reality. There's a physical reality that represents mass. Height is also a physical reality. The acceleration of the object is a physical reality. The potential energy, I don't think, is a physical reality. It is just a placeholder for the relationship between the physical realities that do exist. That's how I understand it, and I noticed that I'm not sure that everybody understands it that way, and I feel like not understanding it that way is confusing. But anyway, so that's what I'm going to say, that the potential energy equals. So this symbol represents potential energy. It's sometimes they use capital P, capital E, but this is kind of the more standard, more traditional type notation, and I like it better. So potential energy is equal to the mass times G times H. So now this is a relationship. This relationship tells you that for any, currently the way we have it set up, we have one thing equal to something else. But what we could have said is we're actually considering the relationship between mass, G, height, and potential energy. So if you wanted to mathematically, you could set this up. I don't know if this will be more confusing or helpful, but if you divide both sides by U, you have M G H over U equals 1. So this, to me, it's not as helpful. I think it's easier to think of it in this terms, but as far as descriptively trying to explain what I'm saying, I think it might be helpful to just show it this way briefly. So what we actually have is we're saying that if we take these four values, mass, G, height, and potential energy, and we do set them up mathematically like this, where we multiply these three together and then divide by this fourth, the relationship between these four values in physical reality should always be equal to 1. Okay? And so just again to spell that out even further, if you did not know the potential energy, but you knew the mass, G, and the height, you can multiply mass times G times the height to get the potential energy. But you can use mathematics to manipulate these to see the other formulas. And so another formula, if we solve for M, we have M equals, so we divide both sides by G times H. We're going to get U over G times H. But let's say that we want to solve for G. So we solve for G, going to take U and divide it by M times H. Now let's say we want to solve for H. H equals U divided by M times G. And so now you'll see, so all this right here is called potential energy. And I'm not gonna, do I want to label it? I'm not gonna label it. I'm gonna consider this base formula, like the way the relationship is standardly memorized, as the label. Although if I was to be more mathematically consistent with my explanation, I would have labeled it mgh over u equals 1. But since that's not the way that I memorized it, nor the way that anybody memorizes it, and I think it may be a little confusing to see why is there a 1 there when it seems like there's no 1 in this one. So I don't want that to be confusing, so I'm not going to put that as the label. So call this the label. So the basic idea then is we have this relationship. So this whole bubble here represents a relationship. And in physical reality, if all we have is this block, and then we're dealing with a situation that's on Earth, not dealing with like outer space, but on Earth, then this is the relationship between these values. And for practical purposes, you can use, if you have any three of the values, you can use the three that you have to find the fourth one that you don't have. So if you know potential energy, G and H, you can solve for mass. If you know mass, G, and height, you can solve for potential energy. If you know potential energy, mass, and G, you can solve for the height. And finally, if this one would be useful as an experiment to use to calculate G, since G is a constant value, calculated value, typically you have to have a value for that. So if you could calculate the potential energy a different way other than this formula that requires G with some formula that did not require G, then divide the value that you get for potential energy by mass times height, you would calculate the value for G. So this one could be used to calculate for G. And so this is the relationship that is mechanical potential energy. So let's consider another relationship. And we're going to deal with our block again, this same block, this 5 kilogram block. And this time, so let's say we have our block. Oops, let's not do it that way. Alright, so we have this block. Once again, this block is going to be the same 5 kilogram block, which it could have been any value, but for now I guess I could solve this up here so that I make everything else concrete. So I'm going to round 9.8 to 10, so this is going to be a very rounded number, but it'll make the math a little easier. So mass is 5 times 10 is 50 times 2 for the height. 50 times 2 is 100. So we're going to say that U in this scenario is approximately 100, even though that's really far off from because of the way that I rounded it. But let's just say it's about 100 joules. Yeah, the unit for energy is, I didn't go over units just now, but it's just the way that, so 1 joule, this is equal to, it's made up of the base numbers, so it's just the unit more or less stands for the relationship. So a joule stands for meters times meters per second squared times, no, sorry, this was kilograms. Kilograms times, well, here, we'll just write it out. Kilograms times meters per second squared times meters, which is going to put meters squared on top. So 100 kilograms times meters squared per second squared is the same as 100 joules. This kilograms times meters squared per second squared is equal to joules. But anyway, I'll get rid of that last part on the end, just to avoid clogging up my little kind of diagram that I'm making here. But so from our setup, we saw that in this scenario, the potential energy was equal to 100 joules. So that means 100 divided by 9.8, or as before, I rounded it to 10. So 100 divided by 10 times 2, 10 times 2 is 20, 100 divided by 20 is 5, should equal 5 kilograms. And that's true, mass is 5 kilograms. And you can do that for any of the others and see that the values hold true. So now let's get to this one down here where we have our mass, but in this case we don't want our mass to be kind of hovering as it was before. We want it to be actually moving. So if the mass is moving with a certain velocity, and I don't know, let's say 10 meters per second squared, which I don't know what that is in miles per hour, so I don't know how fast that is. Let's say it's sliding across ice, just because that's probably going to be a realistic scenario regardless of how fast or slow it's going. So, so this is our velocity of our block, and that's the only other one we need for this. So we have a situation. There's a block. It is moving in a direction, let's say sliding across ice, with a constant speed, or velocity, which is speed with where you also consider direction, and this velocity is 10 meters per second. So the relationship that we're going to consider here is for kinetic energy. So kinetic energy equals 1/2 mass times velocity squared. Now, so what this is telling us, again, mass represents something in physical reality. Velocity represents something in physical reality. I'm not convinced that energy ever represents something in physical reality. I believe it is just a mathematical construct that happens to make formulas work. I guess I'll just say it that way. I mean, obviously it must represent something in physical reality for formulas to work, but I don't think that it doesn't have to represent what it appears to represent. So I'll say it that way. And that's what I believe is going on here. I don't believe there's a something that exists. There's no physical thing that exists, as best as I can tell or understand, that represents this thing that's happening. It just happens to be that the mathematical construct of these values we can call kinetic energy, and it will become useful to treat that as though it's real later. And I think this is an important thing that, again, is often missed in physics. When you apply mathematics to reality, it does not matter sometimes whether the mathematics itself is real, just that the mathematics itself is useful. So the 5 kilogram block is real. The fact that it is moving is real, but the general, how to say this, the apparentness of reality does not tell us that kinetic energy is real in the same way. It just so happens to be that mathematically it is real in the sense that it is useful. Mathematics only needs to be logical, consistent, and useful. It does not need to be real. So it may be real. I could be wrong that this is real, but I'm not wrong that it doesn't have to be real. So, okay, so anyway, back to what I was doing before. So this, once again, is a relationship. What this relationship tells you, if you happen to know the value that represents the kinetic energy of a system, which once again, I don't believe represents any physical reality of this system. There's no such thing as energy, as if the system has more of something or less of something. It's just the mathematical representation of the other values combined. So kinetic energy is a mathematical relationship between mass and velocity. Potential energy is a mathematical relationship between mass and height. So anyway, in this case, the kinetic energy of this block is equal to 1/2 times the mass times the velocity squared. Or, if you manipulate these around, you'll see that 2 times the kinetic energy divided by mass, and then take the square root of all of that, equals velocity. You'll also see that, let's solve for mass. 2 times the kinetic energy, oops, that's supposed to be kinetic energy divided by velocity squared equals mass. Okay, so all of these right here are different ways to explain the same thing, which is a relationship, a mathematical relationship of a physical reality that is useful to consider so that you can make predictions about reality. So the one typical, oh, and I guess once again I could have plugged in the values. So what did I say here? 10 squared is 100. 100 times 5 is 500. 500 divided by 2 is 250. So in this case, the kinetic energy equals 250 joules. And I should have kept the other units up here, but I did not. So writing that out in like the base units that form the unit joules, because again, I don't think that joules exist. Joules is a representation of the relationship of the other quantities that it is built off of. That's how I understand the situation. And so that's what I'm explaining. That's how I'm explaining it. So we had mass is going to be kilograms times meters squared times meters per second squared, which is meters squared per second squared. So this would be 250 kilograms times meters squared per second squared. And you'll see from up here, which I erased, but if you remember, what I had up here was the same thing. 100 kilograms times meters squared per second squared. So the base units are coming from realities that exist. Kilograms, meters, and seconds. Those are based on reality, kilograms, meters, and seconds. But when we take those things based on reality and extend them to something that is purely mathematical, the concept of energy, kinetic energy here, and potential energy here, then we can see that two scenarios that seem very different have a mathematical relationship, because this equals to joules and this equals to joules. So what that's telling us is this situation where this block, which is hovering, or you can imagine it being held there. Conceptually, for me, what is the most clear is if I imagine it being held by a thin string that's like hung, suspended from the ceiling, for example. So it's 6 meters or 2 meters off the floor, which is roughly 6 feet. Yeah, it's roughly 6 feet. So it's about as tall as an adult male, and it's that high off the floor, but it's suspended from the ceiling by a thin string. So, and then energy ends up relating to work in such a way so that if you wanted to think of potential energy as having a basis in reality, it would have to do with what will happen when you cut that string and the potential that it has to do work. But once again, even with work, I don't really think that there's necessarily one-to-one correlation with reality. I think it's better to think of it as a relationship built off of parts. So the parts, again, can be built off of mass, height, and this acceleration caused by the force of gravity. So those three things, or you can build energy off of you can build the concept of energy off of mass and motion, a motion of an object. And so this gives us a way to compare something that is moving with something that is not moving. And that's really the key of why this becomes useful. And so now let's talk about the relationship that kind of ties these two concepts together. And the relationship, I'm just going to spell it out this way. So we have potential energy initial plus kinetic energy initial equals, it's supposed to be K, potential energy final plus kinetic energy final. And what this relationship is telling us is that as whatever the comparison between, I want to say proportion, but that's not going to, I don't know if that's exactly the right word. Basically, as potential energy changes from here to here, from the left side to the right side, kinetic energy should change disproportionately. So if potential energy goes up, in order to keep these equal, kinetic energy must go down. If kinetic energy goes up, potential energy must go down, and so on for the other possible ways that happens. This is a sort of a mathematical description of reality. So they say that the energy is converted, but again, I don't know that that's really the best way to say that, because I don't think that energy is a thing that exists, but the energy, the proper way to mathematically describe the energy changes from one form to another. And so I don't think I'm going to explain that any further, but let me just fill this in now. So since we know potential energy and kinetic energy are equal to these values over here, according to these relationships that we came up with earlier, we know that potential energy initial is equal to mass initial times G initial times H initial. And I'm going to be really pedantic and write that all out, even though typically you would only consider H initial because you think of the mass as being constant and G as being constant, but does not have to be so according to the mathematics. That would have to be so according to the constraints of reality given on the problem, and the constraints of reality given to the problem may change depending on the physical circumstances. So I think it's better to write out the whole thing. It's maybe not better on a problem because it takes a lot longer, but so this is mass initial times G initial times height initial plus, now we're going to fill in kinetic energy. This relationship represents kinetic energy. 1/2 times mass initial times velocity initial squared equals, now we're going to do the same once again, except these times both final. So mass final times G final times height final plus 1/2 mass final times velocity final squared. And one trick to show really quick, just because I'm trying to be about as pedantic as possible, mathematically what you can do here is you'll notice that there is mass in both of these terms. This is a term and this is a term. Both of them have mass initial. This is a term and this is a term. Both of them have mass final. You can factor out the masses, so mass initial times G initial times height initial plus 1/2 times velocity initial squared equals mass final times G final times height final plus 1/2 velocity final squared. Now this is another, this and this are the same. They represent the same thing. As far as the relationships go, nothing has changed between this and this. The only thing difference is the way that we are viewing the relationship at the moment, which is only useful. It doesn't mean anything different. It's just useful for gaining understanding and for seeing applications and solutions involving these values. So another thing that is useful to manipulate these, but where logically there's been no change to the system, but the system can be viewed and understood in a slightly different way, is to solve for any one of these variables. There's a lot of variables here. I don't know yet if I'm going to solve for all of them, but let's just move from the left to the right. So let's say that you know all of the variables that are given here. You know you have physical values for all of these except for one. And let's first say that the one that we don't know is mass initial. Once again, typically in a problem, mass initial and mass final would be considered equal to one another, because usually you don't deal with a situation where the mass changes here. In fact, I'm not even sure how, if you could, I'd have to think a little bit more about it, because there might be other properties that you would have to consider if the mass were changing. But at any rate, just for being mathematically consistent, I suppose, you don't have to think of it that way. So let's say if by some strange magic the mass were able to change according to the rest of this being able to fit with reality. If we solve for mass initial, we get mass initial. We just need to divide both sides by this in parentheses. So mass initial is equal to mass final times G final times H final plus 1/2 V final squared divided by this. G initial H initial plus 1/2 V initial squared. So this, if we had everything except mass initial, this would tell us mass initial. I could do the same for mass final. I think I'm not going to, because literally it'll be the same. I'll just divide both sides by this in parentheses and move it over here. But let's say that mass initial was equal to mass final. Wait, can we do that? Then it's just going to cancel out. So if mass... Yeah, let's not do that just yet. Let's say... Well, I think in most cases that would be... I will go ahead and do that, but let's continue on logically without me actually writing it all out and consider these other ones. So if I wanted to solve for G initial, I would take both sides. There's no G initial in any other term, just this one term here. So I would subtract this over here, so I would get mass final times G final times height final plus 1/2 times mass final times velocity final squared minus 1/2 mass initial times velocity initial squared, all of that divided by, I think I was solving for G, so mass initial times height initial. That would tell me G initial. But let's, and you could do that for every term, every single variable in here. But let's take this and make it a little bit more consistent with reality and say that G is the same for G initial and G final, and to say that mass is the same for mass initial and mass final, because more commonly mass is the same. And actually I did think of an example where mass would be different, and that's when you have something that sticks to something else as it's moving. But let's just say that they're both the same. So in this case we can drop the subscript. So we have mass times G times height initial plus 1/2 mass times velocity initial squared equals mass times G times height final plus 1/2 mass times velocity final squared. So in this case, mass is always the same, and G is always the same. Now, one thing that we can actually simplify this further the way that it is you'll see that every single term has mass, which if we take it to the setup I had earlier, although it doesn't have to apply to this, but let's say we're dealing with these scenarios that I had earlier, although except velocity in this case would end up being in the downward direction, but just at least dealing with the same block. So we can imagine this is our 5 kilogram block, and our 5 kilogram block was true both in the initial conditions and then in the final conditions. So there's some change that happens during this equal sign, more or less. I mean, that's about the best way I can explain it. So let's say we divide every term by m. All the m's cancel out. So this is going to be equal to G times H initial plus 1/2 V initial squared equals G times H final plus 1/2 V final squared. So you'll see that now, so if we have a situation where we want to compare the initial height and initial velocity with the final height and the final velocity, we don't even need to pay attention to the mass because it canceled out. And you notice I skipped over G because let's say that G is always the same, since in reality G will always be the same if this were a physical setup close to the center of the earth. This would be 9.8 meters per second squared, the same as 1/2 is always 1/2. So the only things that are changing now are height initial, velocity initial, height final, velocity final. Now we can assume that now we can solve this for any one of those, and that's how you would actually use it. So where can I fit those at? I think I can fit those down here below. So let's say we wanted to know height initial. So we had an initial velocity value, we had a final height value, we had a final velocity value, we did not have an initial height value. So we're going to say height initial equals, and you would just solve this by moving things around algebraically. So we have g h sub f plus 1/2 v sub f squared subtract 1/2 v sub I squared, and then we're going to divide the whole thing by g. So this is what you could use if you had a situation where you knew final height. So in this situation, we're going to have to think of velocity going in the same direction as the height. Actually, you know what? I think that ends up not being true. I'm not going to try to prove it here, but I do believe that that's actually not true. I can't remember for sure. I feel like it doesn't make sense to me, but I actually think that it's not true that they have to go in the same direction. But let's just imagine them going in the same direction at any rate. So let's take this top picture, and in this case our kinetic energy will be this block that's suspended above the earth, moves downward toward the earth. And what we can do then is, if we know our initial height, which if it's the same block that I drew in this top picture, our initial height's 2. No, let's say we didn't know the initial height. Let's say we knew everything else. That's what I have set up here. So if we knew the final height, so let's say it starts to fall, and at some point we imagine it stopping. Like, it doesn't necessarily stop, but that's where we stop thinking about it moving. And then we know the final velocity, which would be the velocity at that point where we think about it stopping moving. It doesn't stop moving, so the final velocity is not 0, but it's the point where we stop thinking about it moving. So at that point, we don't want to think about it moving anymore. We want to imagine we did a freeze frame, and at the point when we freeze frame, what the velocity of it was right at that moment. Okay, and initial velocity, the same. In this case, when I talk about it being suspended by a string, if you cut the string, then the initial velocity is obviously 0. But if you imagine that it was already moving before we considered it, the initial velocity is the moment that we started considering it. So maybe prior to that it was moving, and maybe it was accelerating, maybe it wasn't accelerating. In this scenario, it will be accelerating. It will be accelerating towards the center of the Earth. So it's an object falling. It's accelerating towards the center of the Earth. We take a freeze frame at a certain moment, and at that moment, whatever the velocity is, that's what we consider the velocity initial. And that at that moment where the velocity initial happens, that's the height initial that we're trying to find. Okay? And then we imagine that this thing falls for a certain amount of time, although we don't have to think about time for this mathematically in this relationship, but we imagine that for a certain amount of time it falls. And then after a certain amount of time passes, we do another freeze frame. And the second freeze frame is when the object, we think of the object as reaching its final destination, you could say. So that's what we'll call height final, wherever that height from the ground is at that moment we made this imaginary freeze frame. And then the velocity final, whatever the velocity of the object was at that moment we made this final imaginary freeze frame. So if we know those values, then we can find this value, this height initial that we did not know, which was the height when we made our first imaginary snapshot. Okay, and using all of the same concepts that I just described, you can solve for the other variables here. So I'll just do that real quick. So velocity initial equals, we're going to have g times height final plus 1/2 velocity final squared minus g times height initial times 2. All of this times 2. And then take the square root of all of it. So that formula would tell us the velocity initial. And what's next here? We have height final. So height final equals g times height initial plus 1/2 times velocity initial squared minus 1/2 times velocity final squared divided by g. These values and with this relationship between them would yield for us the final height, that is the height that it reached for our second like imaginary snapshot. And then the last thing to solve for is velocity final, which is basically going to look exactly like this, except with the finals and initials switched around accordingly. So velocity final, I'm also going to run out of room, equals, I'm going to write the square root sign first because I know it's going to go there and I'm going to run out of space. It's also going to have a 2 again. So let's go back to this. So we have this one right here, g times height initial plus 1/2 velocity initial squared minus g times height final and then times 2 and then square root. So these 4 very useful relationships come from this. So let me get another color here. So these 4 very useful relationships come from this one very useful relationship that comes from these 2 very useful relationships dealing with this one physical object that is relatively close to the center of the Earth, as in like dealing with normal human existence distances from Earth. So yeah, we start with this object, we place it in like basically within the Earth's atmosphere where people live, and we consider these other physical properties of the object as well as these mathematical constructs that are imagined properties of the object. And when we manipulate the combination of the physical and imagined properties and their relationships, along with this property here that is somehow based off of both the physical properties of the object and the mathematical properties of the object, which I'm not going to go into that tangent at the moment, but we take our relationships that we had and we put them into this relationship. It yields us these 4 new relationships that are not really new because mathematically this is all the same. It's just according to the rules of mathematics, this is equal to this, but it's easier for us to use it when we see it this way versus if you have to like work it out and solve it every single time. I don't know if that makes sense. So yeah, so we end up with these a very useful, at this point I would refer to these as formulas. These formulas tell us something that we might want to know about reality based on some given constraints. They allow us to predict a constraint that we do not know based on constraints that we do know. So yeah, there's some physics fun. Oops. Video.